Hi, my name's Ulysses. Today I want to talk about one of my side projects. It's called Gaia, and it's a Rust library for rendering high detail, three-dimensional maps of the world. It's meant for global real-time strategy games like Risk or Civilization, but there are plenty of other applications. In this video, I'll talk about what Gaia offers that makes it unique, how you'd use Gaia in your game, and finally, I'll discuss some of the technical challenges involved in making this library. So first of all, what is Gaia? This is an example app using Gaia. Gaia lets you draw the world as a board game. If you've played Civ, you're probably familiar with this sort of representation. It's meant for games where geography is the primary way the user understands the state of the game. The essential feature of Gaia is that it uses Geographic Information System data, also known as GIS data, to render the world. Where most games use assets created by an artist, Gaia works off of scientific data in order to render our planet with high detail and fidelity. The satellite imagery comes straight from a public NASA dataset, and the topography data, which I've exaggerated, is from NOAA. The cities and country borders come from natural Earth. All of these datasets were imported into Gaia straight from standard GIS data formats. And since Gaia works in this way, I'd say that it's more like Google Maps than Civilization. So how do you, the developer, use Gaia? First of all, I should mention Gaia is meant for games written in Rust that use the GFX crate. If you're not using that, you probably can't use Gaia. Now, there are two steps involved in using Gaia. First, you run a build script, which you can do offline. And second, you invoke Gaia for every time you want to render your scene. The build script is pretty simple. You need to provide satellite imagery, elevation data, and a features file, which will contain your polygons and labels, which in my case, those polygons are countries and those labels are cities. And then, when you invoke Gaia each frame, you provide two things. First, your model view projection matrix, which is used to determine what tiles and features are visible. And second, a set of functions that will determine the visual appearance of your features. They determine the style of your features, if you will. For example, on the screen now, you can see that I'm coloring countries based on their income group. Here's the code that I'm using to style polygons this way. The income_GRP property is from the features file that I provided to my build script. You can see that I return a different color for each possible value of that property. Styling off of properties like this actually gives you quite a bit of flexibility. For instance, here's some other things you could do. You could draw none of the countries of the world or all of the countries of the world. Or you could only draw members of the OECD, a club of mostly rich countries. And also you could just get crazy and only draw the United States of America and have it change color every second. For more details, check out the docs. In this last section, I'll talk briefly about an interesting component of Gaia, how it renders polygons onto an uneven, high-detail terrain. Now, this section will get quite technical, especially with GPU stuff. To illustrate the nature of the problem here, let's look at Germany. We want to find all pixels that correspond to the visible surface of Germany and color them orange. Notice that parts of southern Germany are occluded by the Swiss Alps. Also, though it doesn't really affect Germany, note that some countries can have holes inside of them, like South Africa has a hole where Lesotho is. In typical games, you'd construct a 3D model of your country, and then use standard GPU depth buffer tests to figure out what parts of your model have an unobstructed line of sight. But that won't work here. There are just too many points on the terrain to construct such a model. The vertex buffer with all the parts of your model gets way too big. We want an approach whose complexity is not affected by the detail of the terrain. So Gaia uses a technique described by Schneider and Klein from the University of Bonn. Ultimately, the approach is similar to how most games calculate shadows, where they draw the scene from the sun's perspective and everything that's out of sight is considered in the shadows. So, the exact details here are a bit difficult to explain just in words, but here's a high-level view. You first draw your terrain, ignoring all of this polygon stuff. Your depth buffer now contains information about how far from the camera each pixel of the terrain is. You then draw a prism that goes above and below Germany, a Germanic prism, if you will, and you make sure that it's taller than the highest point within Germany. You're not going to use this prism to actually draw it onto the screen. That would be weird. You're actually going to use this prism to have the GPU calculate all the visible points of the surface of Germany into a separate buffer. You just tell the GPU, yo, draw this prism and use these weird rules about how it is you're going to calculate what to draw. Ultimately, you're going to have this buffer that's non-zero everywhere where Germany is. And then you just tell the GPU, draw orange everywhere as long as the value in this buffer is non-zero at the pixel you're about to draw to. To get a bit more concrete, the exact way you're calculating this buffer is a bit weird. What you're going to do is that every time a front-facing triangle that makes up this Germanic prism fails the depth test, you increment a value. And then whenever a back-facing triangle fails the depth test, you decrement the value at that pixel. It's really hard to believe that that actually does anything interesting, but that actually does calculate this buffer I just described. And if you're interested in the details, you should check out the paper that I've linked in the description. Now, the important part here is that this approach is not affected by the complexity of the elevation model. It's only affected by how many pixels you have on the screen, something that GPUs are usually well calibrated for, and the detail of your polygons, something that you have a lot of control over. Moreover, both of those numbers end up being much more reasonable than a number affected by how many points you have on the elevation model you're using. The implementation of Schneider and Klein's algorithm is actually hosted in a separate crate, totally independent of Gaia, which you can use if you're just interested in that part of this. It's called GFX draping, and I've linked it in the description. And that's all I got. Thanks for watching.